All right. Let me pull up the NMR handout, and we can do that. Let's see. Let's take one of these problems right here. Oh, let's do this one. Well, no, that's not. They don't have enough. Different types of protons. We could do this one if you want. So the matching part is just based on, okay, so there's I think it was in the introductory NMR video. There's one section in there that had a chart. It's in a PowerPoint that I uploaded too. There's a chart that kind of gives you an idea of where certain types of protons are supposed to show up. So, like, say for instance, the carbonyl proton is right here, right? That's this signal right here. And if you notice where it is, it's between 4 and 5. So that's common. That type of proton that's adjacent to an OH group like that is always going to show up in that range between 4 and 5. The aromatics, which are down here, right? Those are always going to be in the same range, somewhere between 7 and 8.5. All right. So if you know those ranges, it kind of helps. The alkyl protons are not as readily discernible because they're all the same type of sp3 type of carbons. But you can look at, like, there are 4 different alkyl type protons on here, right here. Let me pick a different pen. So here, 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 and here. And because none of them are like really extremely close to a electronegative atom or electronegative functional group, then they're all going to show up somewhere between about 0.5 and 1.5, somewhere in that range, right? And that's the range for alkyl proton, really from like 0.1 up to about 1.5. And then they start moving downfield when you put them next to something that's something that's more electronegative, that'll de-shield them. Right, so all of these protons that are circled in blue, they're all going to be down in this area right here.
Okay.
Right, does that help any?
It does.
All right, and if you go back to the PowerPoint that I uploaded, I think there's a section in there that just has the chemical shifts in it. And so starting at 0 all the way down to 10, there's a range for each type of proton. And it's just a matter of kind of, the test is not on responders, so you're not going to have to commit it to memory, but it helps to have it memorized, like where certain protons, you're not going to know all of them, but you'll have an idea of where certain types of protons are supposed to show up.
Okay. Thank you.
Dr. Russell?
Yep.
Can you go over the IR stuff? I never really grasped it fully, so.
Okay. Let me grab this other handout. Where is it? Right. Yeah, here. Okay, so this one has some infrared. Actually, we never did that last example. Yeah, this one has some infrared info in it. So we had the molecule is all messy over here now, but I think I have these notes uploaded so I can erase all this stuff. I think. Nope. I must have just copied the image. But if you look at the molecule itself, right, you see how, so infrared is all about picking out functional groups. And so when you think about an infrared spectrum, what you're looking for is where certain functional groups absorb, right? And so in the infrared video, I gave a list basically of the major functional groups and where they show up. So where alcohols show up, where amines show up, aromatics, alkenes, carbonyls. Those are like your major functional groups. And the thing about it is the absorbance is either going to be strong, weak, or medium, and then broad is another way to characterize it too. So like if we take, for instance, like the alcohol stretch, you can see where it is. It's about, let me see, 1, 2, 3, it's about 3,300, about right up in here, right? So it's about 3,300 reciprocal centimeters. That's the the units for infrared, because you're measuring like the wavelength or the frequency, and frequency is the speed of light divided by the wavelength. So it'll be in reciprocal, because the wavelength is normally in nanometers or centimeters or some unit of distance. So the alcohol stretch shows up 3,300, right? And that's where it absorbs. So the way that infrared works is if you bombard a sample with infrared radiation, ranging from, in that range of wavelengths, a functional group is only going to absorb with a wavelength that matches its own wavelength, or with a frequency that matches its own frequency. So let's say that the alcohol, the OH bond, the bond between oxygen and hydrogen, let's say it's stretching back and forth, kind of like two balls on a spring, right? And it's stretching at a frequency or at a wavelength. It has a frequency, but you can convert it into wavelength. So let's say the wavelength is 3,000 or something like that, nanometers. So when you hit it with this energy, this infrared energy, the only energy that's going to make that bond get excited is the energy that matches it. So that's why you see the absorbances where you see them, because those are the places where the energies match, the frequencies or the wavelengths match, and they excite the bond. So when they get excited, then the motion that's already happening, it gets intensified. So once it passes through that, it absorbs that particular wavelength, it'll be intensified for a short time, and then it'll relax. And then that's what you pick up in the infrared spectrometer. So that's why you see these weird looking downward stretches, because those are the places where functional groups are absorbing radiation, infrared radiation. So on the y-axis, you see is percent transmitted. So it's either going to absorb the radiation or the radiation is going to pass through. So that's called transmitted, right? So that's why you see the stretches that you see. And so for this molecule, you got an alcohol present. So that OH bond is stretching, and that gives us this broad stretch that's highlighted in yellow. And then you also have a long alkyl chain. So you're going to have a lot of alkyl stretching, and that's a really strong stretch. So that's why, and that's those C carbon hydrogen bonds, again, like a spring between two balls, and those two atoms are just pulling apart from each other, stretching back and forth. So when they get hit with this wavelength of radiation, that's what they absorb, right? And so that's what excites that bond. And so that's why you see that stretch. And the fact that you have a really long chain, there's a lot of stretching going on between those CH bonds. So that's why you see the alkyl that's in green. Normally for infrared, like anything below like 900, we just call it the fingerprint region, and you really can't discern anything from that. But what you look for is your major stretches, like the carbon-oxygen bond stretch, which I have highlighted in orange, right? So all of those different stretches show up in the infrared based on the frequencies of the energy matching the frequency of the bond, the molecular motion that's already happening between those atoms, right? So again, this is just a matter of knowing what stretches match what functional groups. So carbonyls have a particular range, right? Somewhere from about 1,700 to 1,800. They have a particular range where the stretches are found. Alcohols have a particular range where they stretch. The OH bonds, NH bonds are in the same range, but the stretch is a little weaker. So it doesn't look the same as an OH stretch, and it's not broad like that, right? So it's just a matter of knowing what shows up where. So did you have a specific question about a specific type of functional group, or was it your question just general?
Not a specific question. It was just like really the concept overall. I just wasn't grasping it, but when you explained, you kind of made it a little bit clearer. So,
all right. Yeah, we didn't spend a lot of time on it. The video that I put together for that, I thought it was informative, but it was just an overview. It wasn't meant to be exhaustive, like to give you all the nuts and bolts. The main thing about infrared is to know where certain functional groups show up in the infrared spectrum. That's the key to that. And again, there's a chart that gives you all the stretches for all the different functional groups, right? But the main ones that you should commit to memory are like the alcohol stretch, alkyl stretch, carbonyl stretch, alkene stretch, CO single bond stretch. Those ones should be committed to memory because you're going to come across those a lot. In this class, anyway, you'll come across those a lot. So those ones should be committed to memory. All right, other questions? Don't not take advantage of this. The fact that we're not having a lecture. You can ask any question about any topic that we've covered leading up to this exam. The bird's talking more than y'all. All right. Any questions about mass spec? Any questions about any other NMR questions?
I don't have a question about the topics, but what worksheet is this again?
I think this is NMR assignment 2, I think. Don't worry about the sequence, but I think this was the first one that I opened. It was like NMR, where is it? If you look on Blackboard, there were 2 NMR assignments that are open. So it's one of those 2. I think it's NMR assignment 2, yeah, and then the other one is NMR assignment signal matching. So those 2 are the only 2 that I opened on Blackboard. But I had like 5 NMR assignments, but I only picked the 2 that I thought would help us the most.
Okay, thanks.
Mm-hmm. Other questions? I feel like I'm in one of y'all's breakout rooms. Everybody just on mute. All right, let me just pause this recording right quick.